Is thesis proposal defense. To say this is a fantastic turnout for a proposal defense. That's pretty exciting. Should take that as a great compliment, Alex. So for those of you that don't know Alex, she's been here for several years, had a very prestigious NSF fellowship. She came from the University of Puerto Rico. The background is mechanical engineering. You're getting people from all across the country. I'm admitting people from the other side of the country. And so she's been here, working with us for some time now. And so she's going to talk about what she's proposing to do for her PhD dissertation. On her thesis committee is, apart from myself, is Larry Mayer, Director of the Center for Coastal and Ocean Mapping, and Neva Gupta in chemical engineering, and Bill Waite from the USGS. And I should say that Alex has spent a fair amount of time down at the USGS working with Bill on things related to what she's proposing to do here. And that's been pretty exciting for us to have that connection, and we're grateful to Alex for making that connection healthy and strong. So I'm kind of excited because I'm looking at Alex, and I'm looking at the thesis committee, and I think we've got a great group of people that has expertise that kind of nicely fits together to form a whole, and that's pretty awesome, I think. So I really appreciate everybody for being here and listening to Alex's proposal defense. And I think with that, Alex, why don't you just launch into it?
Awesome. So thank you, Tom, for introducing me. And I really want to thank everyone for being here today. As Tom mentioned, my name is Alexandria, and today I'll be presenting my thesis proposal, which focuses on understanding the physical properties of gas bubbles in the ocean and how does reality affect what we think we already know. In particular, I'll be focusing on methane bubbles. But before we start, I would like to acknowledge the different funding sources that have funded different aspects of the work that you'll be seeing here today. I really want to thank my committee members for taking their time to be a part of this thesis and to help me through the rest of the journey. And then I would like to thank the many folks here at CCOM, UNH, the USGS, and UC Santa Barbara for helping at different levels, whether it be experiments or just being a part of my life and getting me through this. And also friends and family that are here today to see me give this presentation. So with that out of the way, we can begin our journey with methane bubbles. But before we dive into the ocean, I want to talk a little about methane in the atmosphere. So as we know, methane is a greenhouse gas that contributes to global warming, and its global average concentration in 2018 was measured to be about 2.6 times larger than its pre-industrial equilibrium value in 1750. And so this increase in atmospheric concentration of methane has led researchers to study the various source and sinks of atmospheric methane, whether that be anthropogenic or natural. One of these sources is methane released from the ocean seafloor. And so methane released from the seafloor has been studied for several decades and is spatially distributed across the seafloor, as shown in this map here. Methane is released from the seafloor as either a dissolved gas or dissolved fluid, or as gas bubbles. For the length of this talk, I'll be focusing on gas bubbles because they facilitate the rapid transport of methane through the water column. And so the release of methane from the ocean seafloor can look very differently across the different areas. They can be constant streams of either single-sized bubbles, or they can be slightly more vigorous bubble plumes of different sizes. They can be spatially near each other on the seafloor, and even as they rise through the water column, they can become diffuse bubble clouds. And so as these bubbles rise from the seafloor, the methane from the bubble dissolves into the surrounding water, becoming readily available for microbial consumption, which directly impacts the water column's geochemistry through aerobic microbial oxidation, which then leads to oxygen loss and ocean acidification. Under certain circumstances, though, methane gas bubbles can reach the upper water column and potentially contribute methane into the atmosphere. And so the current estimate of methane flux from the ocean is about 1 to 13% of the global average atmospheric methane budget. And this large uncertainty has led researchers to further assess the environmental impacts of methane bubble release from the seafloor. First, by improving the current capacity for long-term monitoring of methane flux from the seafloor to capture spatial and temporal variabilities, and also by improving the capacity to quantify methane flux and transport through the water column in order to try and narrow the uncertainty in seafloor methane flux estimates. And so the goals of this thesis is to understand how the variations in bubble properties, such as non-sphericity, surface coatings, and external physical processes impact our capacity to quantify methane flux in the ocean and their contribution to the global atmospheric methane budget. So to study methane in the ocean, we often use acoustic systems. These acoustic systems have been used to study methane seeps in the ocean for decades and take advantage of the large acoustic impedance contrast between the gas inside the bubble and the surrounding water itself. And this is what makes gas bubbles excellent acoustic targets. Different types of acoustic systems have been used, such as single beams and multi-beams, to map these seeps due to their ability to map large spatial areas. In addition to using these acoustic systems to map the spatial extent of gas bubbles in the ocean, researchers have used acoustic inversion techniques to obtain estimates of gas flux in the ocean. These estimates, however, rely on analytical scattering models that are derived on certain assumptions about the bubbles themselves. And so we're going to talk a little bit about these analytical scattering models that are used in these acoustic inversion techniques. These models predict how a single gas bubble will scatter sound in a liquid. In our case, we're really interested in understanding how gas bubbles scatter sound in the backwards direction, and this is given as the acoustic backscattering cross-section, sigma bs. Sigma bs is a function of bubble size, which is typically given as bubble radius, the frequency of the incident acoustic wave, and other physical properties of the medium of the gas. And so I just want to show an example of this. And so here we have a plot of the resulting sigma bs for a 1 millimeter radius bubble as a function of frequency for two commonly used models that are used in acoustic inversion techniques. And so this curve is what we call the frequency response of a gas bubble. And if we were to look at the frequency response of a 2.5 and a 5 millimeter radius bubble, we can observe that they are unique. And this uniqueness is what allows researchers to classify bubble responses in acoustic data. However, these models are derived under the assumption that bubbles are spherical in shape. And the question is this assumption valid for methane bubbles in the ocean? And so many field studies, such as the one conducted by Wang et al., have been done to observe the natural bubble size distribution of natural methane seeps in the ocean and show that bubbles can range between 1 to 5 millimeters in radius. And with the use of optical systems, we can actually observe the shapes of these bubbles in nature, and they tend to have non-spherical shapes. In addition to this non-spherical irregular shape, bubbles also tend to wobble as they rise through the water column, changing in size constantly and in their bubble orientation as they rise through the water column, therefore violating the assumption of the analytical scattering models, which gives objective one of this thesis a purpose, which is to understand how variations in bubble shape and size affect the acoustic backscatter from single gas bubbles in order to better use acoustic data to obtain more accurate quantitative estimates of methane flux. And so while acoustic systems have provided researchers with the capability to map methane seeps in the ocean and obtain an estimate of gas flux, these measurements, unless we go out and survey them continuously, only provide a snapshot of the gas flux from the seafloor. So therefore, researchers have really been focusing on developing numerical models to track the dissolution of methane bubbles in the ocean to complement existing measurements. These numerical models estimate the gas dissolution, so just the gas exchange between the bubbles in the surrounding water column, and are used to predict the concentration of methane that is dissolved in the water column and potentially into the atmosphere. And a really good example of this is the work done by Hens et al., where they're tracking different bubbles of different sizes to try to match this acoustic image of bubbles, and at the same time track how much methane is being dissolved into the water column itself. And so these models that are being used heavily rely on physical parameters and properties of the bubble and of the surrounding medium, as well as the bubble size, shape, and the surface coating of the bubble itself. And so when methane bubbles are released under high pressure and low temperature conditions, they can begin to form what is known as a hydrate coating on its surface, as we can see here in this image. And so this presence of the hydrate has been observed in nature and in field experiments, like the one done by Redder et al., where they show that the presence of the hydrate reduces the dissolution rate of gas bubbles as they rise through the water column. This reduction in dissolution rate can extend the lifetime of a gas bubble, aiding them to reach the upper water column and potentially the atmosphere. So therefore, objective 2 of this thesis is focused on understanding how the presence of gas hydrate on the bubble surface affects the dissolution of gas through the water column and how it impacts estimates in coming from the numerical models themselves. And so far we've talked about the current capacity for quantifying methane flux and transport in the ocean, and how objectives 1 and 2 aim to understand the limitations of these techniques. So now I really want to focus on the capacity to monitor methane flux in the ocean over large timescales. The temporal variability of methane flux from the seafloor is an ongoing research interest, and recent studies have hypothesized that methane release can be linked to external physical processes such as tides and earthquakes. This temporal variability can create bias in local and global estimates of gas flux in the ocean and atmosphere. Several studies, such as the ones conducted by Romer et al., have collected long-term measurements of methane flux and/or concentration in order to track the temporal variability of natural methane seeps to correlate them to external physical processes. However, due to low resolution sampling of these measurements, it is difficult to correlate the observed temporal variability to external physical processes. So therefore, objective 3 is focused on establishing a long-term monitoring system to understand the temporal variability of natural methane seeps and their potential causes. And so together, the goal of these objectives is to understand the limitations of the techniques mentioned above and to test how those limitations impact our interpretation of the fate and transport of methane in the ocean. So now I'm just gonna do a deep dive in each of these individual objectives into more detail. And so coming back to objective 1, we're interested in understanding and quantifying the effect that bubble shape and size have on the acoustic backscatter of single gas bubbles. And to do this, I conducted several experiments to compare observational estimates of the acoustic backscatter to several analytical backscattering models. And so before we talk about the experiments and the results from that, I just want to talk about the different analytical models that were used. Here we have the Anderson model, the Klein-Medwin model, and the Asian-Layton model. And these 3 models are typically used in acoustic inversion techniques currently to understand methane seeps in the ocean. So I'm going to start with the Anderson model. So at the bottom here, we have the equation derived by Anderson, and also an example of what the backscatter looks like from this model for a 0.79 millimeter radius bubble as a function of frequency. And so the assumptions that Anderson used to derive this equation were that the bubble was going to be spherical in shape and that Ka is approximately 1, where Ka is just the ratio between the bubble radius and the wavelength of the incident acoustic wave. The second model, the Klein-Medwin model, also assumes that the bubble is spherical in shape. However, this time it assumes that Ka is much smaller than 1. Ainsley and Layton derive a very similar model to Klein-Medwin under the same underlying assumptions. And so, as I mentioned, these 3 models are typically used for acoustic inversion techniques to go from acoustic estimates to estimates of physical properties of the gas bubbles themselves. However, all of these models assume that the bubbles are spherical in shape, which we know that is not also always valid for methane bubbles in the ocean. And so to take this into account, we used a 4th model, the Yi model, which was used to obtain acoustic backscatter estimates from spheroidal bubbles. The model also assumes that Ka is approximately close to 1 in this case. So now that we've talked briefly about the different models that we'll be using to compare to our experimental estimates, I just kind of want to highlight the importance of Ka. And so now above on the top x-axis, we have Ka for this 0.79 millimeter radius bubble. And as we can see, for Ka values that are smaller than 0.3, all 4 of the models do pretty much a good similar job at predicting sigma bs for this size bubble. However, as we start to approach a Ka of a 0.3 and increase above that value, approaching 1 at the end of this plot itself, we can start to see that there are deviations between the different models. And this deviation between the models as Ka increases, in addition to the violation that bubbles are assumed to be spherical in shape, can lead to can lead to biases in estimates obtained through acoustic inversion techniques if the inappropriate model is used in the field. And so to shed some light on this, several experiments were conducted in the engineering tank here, located here in the Chase Ocean Engineering Lab. For those of you who haven't seen it before, it is an 18-meter long tank by 12-meter wide and 6 meters deep. To create single bubbles, we deployed a bubble maker that was developed by Kevin Reichert, a former CCOM master student. The bubble maker was deployed to the bottom of the tank and was used to create single bubbles that range between 2 and 5 millimeters in radius. In addition to these sizes, the bubble maker was modified in order to try to create bubbles that were smaller than a millimeter in radius in hopes to create spherical bubbles. To study these bubbles acoustically, we used several acoustic transducers, the first being a custom-built low-frequency constant beamwidth transducer, which was used to sonify gas bubbles over a frequency range of 8 to 20 kilohertz. In addition to this one, we used two Simrad broadband transducers, an ES120 and an ES200, to insonify the gas bubbles over a range of 90 to 260 kilohertz. All of these transducers were calibrated to correct for transducer beam pattern effects and to obtain estimates of the acoustic backscattering cross-section of the gas bubbles. And so this wide range of frequencies allows us to characterize a significant portion of the bubble's acoustic frequency response and allow us to explore the different regimes of her low KAs and high KA values. And so finally, before talking about the actual results from the acoustic data itself, we characterized the bubble shape and size during this experiment using two imaging systems. The first one being a direct capture device shown here. This capture device collects single bubbles into an inverted graduated cylinder and uses an underwater camera to collect video data to count the number of bubbles needed to fill in a certain cylinder volume. This provides an estimate of the average bubble volume and therefore bubble radius. A secondary camera was used to obtain high-resolution images of the gas bubbles as they were released from the bubble maker to try to give us a sense of the bubble shape. And so 3 different effective bubble sizes were generated during this experiment, the smallest being sub-millimeter in size and the 2 largest ranging around 3 and 4 millimeters. The images shown here correspond to the 3 different bubble sizes that were obtained with the imaging camera. And as we can see, the smallest bubble, although not spherical in shape, had a consistent spheroidal shape. However, the 2 larger bubbles are non-spherical in shape and are irregular as they rose to the field of view of the camera. And so now that we have a sense of the different sizes and the shapes of the bubble that we're trying to study during this experiment, we can go and talk about the results from the acoustic experiments themselves. And so here I have a plot of the estimates obtained for the acoustic backscattering cross-section sigma BS, also with the modeled results given by the curves. The dotted lines, the gray dotted lines, are just the average sigma BS value for all the data collected, while the upper and lower limits correspond to the 95th and 5th percentile estimates, respectively. And so this is for the smallest bubble. And if we looked at the 2 larger bubbles, just highlighting here, the color codes correspond to the different models presented in the plots themselves. We can start to take away some of the results from just looking at the data here. So the first thing that I want to highlight is that for low Ka values or low frequency values, Ka values below 0.5, all of the models perform equally at predicting sigma BS. However, as we increase above 0.5, the deviation between the models grow, and no particular model performs best at predicting sigma BS compared to the experimental observations. Another thing to note is to look at the variability of the observational estimates of sigma BS themselves. And so focusing on the low frequency data, so from 8 to 20 kilohertz, the variability is similar for all 3 bubble sizes regardless of the bubble shape. This variability is linked to calibration offsets obtained from the transducer. If we looked at the higher frequency data, so frequencies from 90 to 260 kilohertz, we can see that for the smallest bubble up here in the top, the variability in the estimates is consistently small, even for Ka values higher than 0.5, except near the regions of 160 and 180 kilohertz in this area right here. However, if we focus at with the two larger bubbles, we can observe that the variability in the estimates of sigma BS grows larger as Ka increases. This increase in the variability in the estimates of sigma BS for larger bubbles at frequencies between 90 and 260 kilohertz can be partially explained by the instantaneous variations in bubble shape and size of these bubbles as they rose through the water column. This variability can be a source of error in the acoustic inversion technique seeking to use analytical scattering models to obtain estimates of gas bubble properties in the ocean. So these results from this objective provides more insight on how shape and size of a bubble affects sigma BS, and will address the potential bias in estimates of physical bubble properties in the water column when using these analytical scattering models in the acoustic inversion techniques. So I just want to note that the results from this objective have been submitted for peer review to the Journal of the Acoustical Society of America. And so now that we're done with objective 1, we can switch gears to objective 2, which focuses on trying to understand how the presence of hydrate on the bubble surface affects the dissolution process of gas rising through the water column. And so dissolution from gas from a bubble into the surrounding water can be simply described with the equation given by West et al., either as a function of time or a function of depth. From this set of equations, we can track the dissolution of gas as a function of different parameters, such as the surface area of the bubble, the mass transfer coefficient of the bubble, the rise velocity of the bubble, the solubility concentration of the gas within the water, and then finally the aqueous concentration of the gas that's already in the water itself. And so out of all of these terms, so I guess the first thing to note is that the question now is, for this objective, is to really try to understand how hydrate on the bubble surface affects dissolution of gas through the water column. And so out of all of these terms that I've just mentioned, the ones that are most dependent on the surface coating are the rise velocity and the mass transfer coefficient. These parameters tend to be given as parameterizations that depend not only on surface coating, but on other physical properties of the bubble itself, such as bubble shape and size. In the case of the mass transfer coefficient, it also is dependent on the rise velocity parameterizations of the bubble itself. And so I want to show some examples of some of the parameterizations of rise velocity and mass transfer coefficient of gas bubbles as a function of bubble diameter that are used in some of the numerical models that I had mentioned before. With these examples, I want to really highlight the impact that surface coating has on the rise velocity and mass transfer coefficient. And so the dashed lines on both of these plots correspond to parameterizations developed for clean bubbles, such that the bubble surface is clear of any contaminant or surfactant, and this allows internal circulation within the bubble itself. The solid line on both of the plots now correspond to parameterizations for contaminated bubbles, or what we sometimes call dirty bubbles. And this contaminated surface dampens or inhibits the internal circulation within the bubble. So as we can see from these plots, clean bubbles tend to rise and diffuse faster than contaminated bubbles, which leads to the question of how do numerical models consider the effect of hydrate coating on the bubble surface? And if they do, how do they do it? And so some of the models have considered the potential effect of hydrate on the bubble surface by modeling the transition between a hydrate-free and a hydrate-coated bubble to be analogous to the transition between a clean and a contaminated bubble. However, it is unclear how the presence of hydrate coating on the bubble surface affects the mathematical parameterizations of the rise velocity and mass transfer coefficient used in these numerical models. To try to understand the effect that hydrate has on the bubble surface and on these parameterizations, I'm hoping to conduct several experiments to obtain measurements of the rise velocity and mass transfer coefficients for both hydrate-free and hydrate-coated gas bubbles. And so the experiments will be conducted at the USGS down in Woods Hole, Massachusetts, and will be conducted using a system that we call a flow loop device. The flow loop device is a closed loop system that circulates water in the counterclockwise direction and captures single gas bubbles in an inverted cone. To study these bubbles inside the flow loop, we use two high-resolution, high-speed imaging cameras that are positioned perpendicular to each other to obtain images using along the X and Y axis of the bubble itself. And so here's just an image, an example image of a small bubble swarm within the flow loop itself. And so these images from the cameras will allow us to obtain estimates of bubble volume as a function of time and provide estimates of the rise velocity. And so the main question is probably that you have is how are we going to form methane hydrate? As some of us know, methane hydrate, in order to create that surface coating on the bubble, we have to operate under extreme pressure and temperature conditions that are actually quite difficult to do in the current flow loop system itself, since we're using acrylic to observe the bubbles. And so therefore, we're going to use xenon as a proxy for hydrate to form hydrate on top of the bubble. And we're using xenon because it shares a similar structure 1 hydrate coating that methane also forms, but we can form them at relatively lower pressure temperature conditions compared to methane. And so in addition to creating the hydrate coated bubbles, we're also going to obtain measurements for hydrate free xenon bubbles, air, and methane bubbles. And so we did a preliminary experiment back in February 29th of this year, which seems like a very long time ago. So I'm just going to talk about some of the preliminary results obtained from that experiment. So to start, I just want to show you an image of a collection of images of a bubble rising through the flow loop. The bubble's rising through a stagnant water column, and we can use the collection of images to obtain the rise velocity of the bubble, as well as the trajectory and the path that the bubble is taking as a function of bubble size. For dissolution, the cameras were configured to collect images every 60 to 90 seconds until the bubble is dissolved. And from this data, we can obtain a time series of bubble size that will give us information about the shrinkage rate or the dissolution rate of the gas bubbles, and therefore use this information to obtain estimates of the mass transfer coefficient. And so here we have some of the preliminary experiments from February. On the top left-hand side, we have the equivalent diameter of the gas bubbles as a function of time. On the right, we have the shrinkage rate as a function of time. And so if we look, we can immediately see that air bubbles dissolve much slower than methane and xenon bubbles. And this is due to the fact that air is saturated in the water compared to the two other gases. And so from the information from the shrinkage rate or the dissolution rate, we can calculate the mass transfer coefficient of the bubbles using the equation shown here. And so the first thing that I want to note from the mass transfer coefficient data is that xenon bubbles have a lower mass transfer rate coefficient compared to air and methane, which is on contrary to what we would expect, since they're dissolving much more quickly than the air and methane bubbles. And this highlights this solubility term here. And this slower mass transfer rate is probably caused because of the high concentration difference in the solubility and the aqueous concentration. And so the dissolution of xenon is being driven by that concentration difference. It's worth noting that the solubility term for xenon is several times larger than that of methane and air, which is helping drive this concentration difference in the equation and what we observe in the data. Another interesting result that we noticed in the preliminary results was that none of the hydrate-free coated bubbles exhibited a mass transfer coefficient that was along the lines of the clean parameterization curves, which are those dashed lines. And this was also observed in the rise velocities. The rise velocities for hydrate-free coated bubbles were in between the clean and the dirty parameterizations. I just want to note that in practice, it is actually very difficult to obtain estimates of rise velocity and mass transfer coefficient of gas bubbles on these parameterizations for clean bubbles. To do so, we would have to use super deionized water in order to get on that curve. And so that just highlights the fact that if we were to generate bubbles using tap water, which was the case in this experiment, or especially in ocean water that have lots of surface contaminants and things that could adhere to the bubble surface itself, the results from that data would exhibit, as we can see, rise velocities and mass transfer coefficients somewhere in between the clean and dirty parameterization curves. Which means, and to relate back to the numerical models that we're interested in using to obtain an idea of where the methane is going into the water column, they modeled the transition between a hydrate-free and then hydrate-coated bubble as a clean and dirty bubble from a clean to a dirty bubble, which is not the case as we can see here. And so from the results of this preliminary experiment, it's clear that the presence of hydrate complicates the dissolution of gas through the bubble. However, it's still unclear entirely how the individual parameters of the dissolution equation are affected. And so the next few steps for this experiment is to collect more data for clean and dirty non-hydrate coated bubbles, in addition to hydrate coated bubbles at various temperatures and pressure conditions, and at similar concentration differences, to further understand how hydrate affects dissolution and how it affects the different parameterizations for the rise velocity and mass transfer coefficients used in numerical models. And so moving to the last objective, we're going to talk about what we're doing as far as establishing a long-term monitoring system to study the temporal variability of methane gas in the ocean, and also how they can potentially be related to external physical processes. And so for this, we're going to move to the West Coast, down to Santa Barbara, California, and we're going to look at the Colloid Point Seep Field, which is known for its prolific natural hydrocarbon activity. And it's often dubbed the most spectacular hydrocarbon seep field in the world, in my opinion, with reason. As we can see in this video, this site has been studied for several years to understand the spatial and temporal variability within the seep site itself. And it has also been a hub for interdisciplinary research to try to understand how these hydrocarbons affect the biological system and chemistry in the water column itself. And so between the years 2016 and 2017, a group of us had the opportunity to survey the Colloid Point Seep Field and map the spatial distribution of seeps within the area. One area in particular that kind of caught our attention was a patch of high seepage activity near a decommissioned oil platform known as Platform Holly. And so this platform gave us the opportunity to potentially set up actually set up a acoustic monitoring system on the platform itself to observe the high seepage activity in the area. And so with this acoustic survey, we determined that we were going to focus our efforts and mount an Simrad ES200 on one of the cross members of the platform to look at the westward plume from the platform itself to monitor the spatial and temporal variability of this seep. And so on the cross member itself, the transducer is mounted on a pan and tilt system. The system was programmed to pan over a large range of angles to capture this large area, and also the transducer was held at a 15-degree declination angle facing towards the seafloor. And so this acoustic system has been collecting data since early September of 2019. And I just want to show a couple days worth of data. Here we can see the seafloor, and I want to highlight that this color bar is just the acoustic intensity in dB. So that tells us how strong a scatter is in the ocean. And so we can see the seafloor, but more importantly, we can see this plume structure. And in this data, we can start to see the spatial variation, spatial variability of the seep. It moves within the water column. And also, if we looked at the color of the acoustic intensity, we can begin to see this temporal variability in at least in what we would relate back to the flux of the plume itself. However, due to some malfunctions, the pan tilt system stopped working, and so the transducer itself is now held facing towards the westward direction of the plume itself. And so this narrows our point of view of the plume. However, even in this narrow point of view, we can still see spatial variation and also temporal variation in the intensity of the plume itself. And so this acoustic system is currently transmitting a broadband signal every 10 seconds and has been collecting data, as I mentioned, since early September, which means that to this day, we have more than a year's worth of high temporal resolution data of the seep just within the vicinity of Platform Holly to process and analyze. And so I just want to show 2 days worth of data. Here we have an acoustic echogram. On the x-axis, we have time. On the y-axis, we have the range. And then the color bar, again, is just the acoustic intensity in dB. And so from this data, we can already identify 3 main regions: the near plume, the far plume, and the seafloor. In the near plume, we can see some seepage activity, but the majority of the activity that occurs within the far plume itself. And so we're going to be focusing a lot of our preliminary efforts on understanding the seep within this far plume. And so I just want to zoom in and highlight the spatial variability. If we were to look at the maximum peak of this plume itself, we can see that it has a cyclic motion already just within the 2 days. And I want to highlight that the bubbles that are being studied within these ranges have traveled through the water column already for several meters, which means that they're going to be influenced by tides and or currents, as we can begin to see in the data itself. And so this is still a new project, and the next steps for this study is to really determine a path forward to process and analyze the data and convert these acoustic measurements into estimates of gas flux. And so once we obtain estimates of gas flux, we can start to create a time series of the gas flux and the position of the plume as a function of time, and correlate them to other physical properties such as changes in tides, currents, earthquakes, atmospheric pressure, that could potentially give us a sense about the movement of methane within the water column and potentially provide insight on the release of methane from the seafloor. The environmental data that we'll be using to correlate the external physical processes to gas flux will be acquired from available public data sampled within the vicinity of the Colo Point seep field. And the results from this study will hopefully provide insight on how the temporal variability of natural methane seeps and how to monitor them in the future and how they're potentially correlated to external physical properties. And so the outcomes of each of the individual objectives of this thesis will hopefully provide insight on how bubble properties such as bubble shape, size, and surface coating affect how we implement the models that we use to obtain estimates of gas flux in the ocean and how we propagate that into the atmosphere, and also provide insight on how the temporal variability of gas flux in natural seeps and how this variability is related to external physical properties. And with that, I would like to say thank you for being here again today, and I'm ready for any questions.
Thank you, Alex, for that presentation. Super interesting. Having spent some time working with the flow loop trying to make single bubbles, there is definitely an angry way to say bubbles. I'm the rest of the presentation I'm totally in line with, but okay. So I think at this point, now that Alex has kind of described to us sort of the breadth of what it is that she is looking at, I think it is now time just for sort of an open discussion and open questions here. So I think if you are in the, I'm trying to think about what the easiest way to do this is, since we're not all sitting in a room together. And I kind of think that maybe what makes sense is for committee members, I think that you're welcome to unmute yourself and just fire away. And then we're getting questions from the audience in the chat, and I'm happy to share those with you. And maybe to just kick things off, and anybody can interrupt me at any time, by the way, maybe to kick things off, we can go back to slide 24. There's a couple questions from the audience, and they sort of match some of the questions I have for you too. So maybe slide 23, actually. You have a slide where you have some of your, I guess I'm missing the slide, but you have a slide where you have some of your results for different bubbles, air bubbles and methane bubbles that you collected down at the USGS, and it has your data. Yeah, that's the one I was thinking of. So we had a question from Ruby Fu. I believe formerly of MIT, a Ruben Wannis student, I think. It's
Yep.
great that to see her on here. And she's asking you what the dashed lines are on the lower left part of this slide. She actually has the slide number right too. It was my mistake. So those dashed lines in the lower left figure.
These ones?
Yep.
So if these are parameterizations for clean bubbles, so these are just the mass transfer coefficient and rise velocities for clean bubbles. Right now I don't remember which parameterizations. There's several of them. And so I can actually just look. It's probably Bird et al. And I know Leifer and Patro was this one, but yeah. So the dashed lines are just the clean bubble curves.
Okay. They're a little irregular looking, at least down below 2 millimeters or so in diameter.
Up here?
Yeah.
Yeah. So that could either be a me with MATLAB mistake, or that could just be the way that a lot of these parameterizations work is that they have different size ranges for which they have empirical equations. And so you just kind of match them.
So this, I guess, I don't know, in terms of, I feel like I'm asking questions that maybe there's no answer for yet. But just thinking about these two, you've got the dirty bubble down below in the solid line and the dashed line. I'm looking at the same figure, the dashed line for the clean bubbles. And I get the relationship. I get why those are different in terms of, you know, the flow and the boundary layer of the flow and whether or not the gas is recirculating inside or if it's just sort of rising like a slug. And your data and lots of data are in the middle someplace. Yep. And so what explains that? Like, what are your thoughts about that? How do you get in how would you describe what's going on with the bubble such that you would get results smack in the middle of those two places?
Yeah. I guess intuitively, the first thing I want to think about is there's the idea of what partial contamination is. And so a lot of these kind of fall in that, like, potentially they're, so I guess the thing for me is that a contaminated bubble kind of assumes that the complete surface is completely immobilized. So it's completely covered. And so my first reaction is, if I think of a bubble that's being generated in a tap water system like ours, you might have salts and surfactants, but they don't necessarily create a rigid surface. And so you might have pockets of areas that are still clear to, like, it's not covered, it's not completely dirty. And so that's my first initial reaction, is to think that potentially it's not a completely rigid sphere that inhibits the internal mobilization of the gas itself inside the bubble. And then there's the idea of spherical caps, and that has some effect, but, you know, when we think about clean bubbles, that's probably not the case. Hydrate-coated bubbles maybe, when they start to form. I'm not sure if that answers your question a little bit.
It does. That's certainly interesting to think about. And I guess one of the things I was wondering is what the effect of shape would be. And I know that there are some, there is and we've talked about this paper before, but there was this paper that was a compilation of results.
Yep.
And they basically showed, it was sort of, they had both, you know, the clean and dirty bubble models on there and everyone's data, which basically just fills the area between those two. Yep. And I was wondering if that holds true, you know, to what extent shape plays a role in terms of changing the you know, that boundary condition and the flow. And I wonder if you could maybe explore that as part of your experiments, because you can control shape by creating different size bubbles, right? You can, yep. You know, do these models do you tend towards one end member or another of those models for very, very small bubbles? Maybe, I don't know. It's just a thought.
Yeah, that's a good question. And I think when we look at those rise velocity plots, when we think about like field data, and you have your rise velocity for clean and dirty, and they're all just like speckled in between, a lot of those models are already they take to a certain extent the shape, because they're divided into the different regimes. So you have like a regime that for smaller than maybe 1 millimeter, 2 millimeters in diameter, they're assuming that it's spherical, and that for larger diameters, they're already assuming that it's ellipsoidal or irregular in shape. I've tried looking for papers to try to see what like of ellipsoidal bubbles. I haven't found a lot, and it would be worth looking into. And I feel like we can do that in the experiments. Just have to be very careful when we generate the bubbles themselves.
Yeah. Okay. Thank you. And again, to folks to Bill, or you guys feel free to chime in and with questions. I see Bill unmuting himself. So
I was wondering if you wanted to look into the chat. The chat's got a whole bunch of questions sort of queued up there.
I will look, and I do have that open, and we can go there. So let me see if I can go through and do these sort of in a combined way, at least for what's there now. You have a ton of great questions here, actually, Alex. And so let's go to questions that originally started with Jack Deb, which I sort of started to answer. I can't help myself, apparently. And one of the questions he started with was, do you know basically what the gas is in the bubbles? Is it pure CH4? And he's making the comment that in wetlands, ponds, and lakes, they can often be a mix of CO2 and CO4.
Yeah. I'm assuming this is related back to either to objective 2 maybe, or objective 3. If it's related to the experiments within the flow loop device, we assume that the methane is pure. But if we're talking about like platform Hawley, I don't actually know if the methane released from the seafloor there is 100% methane, or if it's a mix. But I feel like that's something that we could find an answer to with some of the people down at the University of California, Santa Barbara. They've done a lot of chemistry down there, and they have a lot more information about the plumes itself in the vicinity of that platform. So we can answer that question. I just don't know what it is right now.
Yeah, my suspicion is it's got some other hydrocarbons in there as well. And he followed up with that question, actually. And I think he is thinking about natural systems rather than your experiment.
Yep.
And so let me just read what else he wrote. Expanding on my initial question, 2 reasons I was wondering about what gas is actually inside the bubbles. 1, does the gas impact the acoustic backscatter, or is the difference between water and any gas the main driver of the acoustic intensity? And, there are implications for missizing the bubbles there that he's pointing out. And the second part of that question is, even if the size estimates are not sensitive to the composition of the gas in the bubble, converting to an estimate of the methane flux I'm not following the rest of it, but I think he's basically saying if you just assume it's all methane, even if your acoustics don't, your acoustic response doesn't make a big difference. You can't really just assume it's methane, or you're going to have some rather large errors there, or have some large errors there. You want to comment on that?
Yeah, I do. So for the first question, the first part, gas can impact the backscatter. We have. I don't have it clear in my mind right now, but I have seen plots where we're looking at CO2, argon, methane, nitrogen, and air, and we can see shifts in the backscattering cross section. So that original sigma BS curve, there are differences, and so if you don't have a good sense, that could impact. But it depends on how far off you are probably. As far as question 2, I think this is a great question in the sense of it just goes to show that with the acoustics alone, it's very difficult. You have to have some sort of sense of what the gas is at some point, whether that be at the seafloor or at some depth, and use that to use the acoustic data and understand how that's going to be affected, and using the numerical models to kind of complement that. I feel like maybe I didn't answer that question.
No, I think this is Jack.
Okay.
I'm sorry, I wasn't supposed to unmute myself, Tom, but
Oh, you're welcome to.
It locked me out, so I thought I'd take advantage. No, I mean, I think it's a really complicated problem, and I think what you're proposing to do is outstanding. But I was going to say that Ruth Varner and her group and Mike Pallas have been looking at this to try to quantify methane and CO2 fluxes out of lakes and ponds and all this, and they might have some ideas about how you could have some more confidence at a place like Santa Barbara, the coral tar seeps or whatever, ways to catch the bubbles and actually figure out what they are if people that already out there haven't done it.
Yeah, that's a good point. Good point.
And just to chime in there, so we work with Dave Valentine out there, and I think he and others, I think a lot of people have worked in that area and have probably, I do think that they have data on what the gas composition is in the bubbles at the source. That is a real tricky thing with acoustics, that we have that ambiguity between, is it a different gas composition or is it a slightly different size? And that's really difficult to sort out acoustically. It's not a measurement
trivial
that we can make independent of other information.
Another thing that I don't know if you could do, but maybe your collaborators could do, is try to capture the gas right at the seafloor, and then also try to catch the bubbles when they hit the surface and see how much dissolves, and that that all makes sense with the other parts of what you're doing, which would be a way to close the loop,
Yeah, and I know they've done some some field deployments on monitoring. They collect methane samples, profiles in the area. I know that that's data that's available too publicly. So that could be good to use when trying to get a gas flux estimate too. Yeah, thank you for that question.
Yeah, good questions.
And this is Larry, I'll just chime in and say that there's been a lot of work done by people at Mabari in terms of capturing exactly the experiment that Jack described, capturing gas at the seafloor in a chamber that maintained pressure, and then looking at its differences as it rises. I can give you some of those references.
Yeah, that would be great.
And I think Tom was right. I think in this general area, there probably won't be much or any CO2 really, but there are many different types of hydrocarbons. So.
Yeah. Yep. So tricky. And not something to look at just from the acoustic perspective alone, for sure. But really, it's a really interesting line of questions there. So I'm looking down the list at other questions here, and there's a question from someone named Liz Widener that says, "Nice job, Alex. I was wondering," I'm just joking, we all know Liz. "Nice job, Alex. I was wondering in objective 1, what was up with your measurements of the 0.79 millimeter bubbles between 100 to 60, 180 kilohertz. Why is the scattering level so much lower than the models?" Yeah, this must be what she's referring to here.
Yep. So the first initial, I guess the main thought is that this is likely caused by interaction. So additional resonance for higher order modal resonance in the bubble itself that could be lowering this, given the response here between 160 and 180 kilohertz. The models such as like the Anderson and the Yee model are able to model these higher order modes, and it's potential that it's linked to those. the presence of those modes.
I kind of have a related question to that too, and that is thinking back to Scott Loringer's work, where he was looking also at fluid models for backscatter or backscatter from fluid inclusions. He's looking at oil droplets that were definitely ellipsoidal, and he was able to show some nice, that the theory and the nodal structure or modal structure kind of looked like you could see those dips really clearly in his data. They're quite beautiful looking results, actually.
Yeah.
And I happen to know, I don't even present it here, but you don't really see those for these bubbles. Like when you look at the models for Ye or for Anderson, which, these aren't really spheres, they're spheroids. So maybe Anderson isn't even correct, but even for Ye, you see that you do have some substantial modal structure. Your data actually go in the opposite direction of that, and they're extended over a wider range of frequencies. And I think I've heard you say that on any individual backscatter observation, a single one from a bubble, you don't see that modal structure. And I'm wondering what you think about that and why is that? It would be really comforting to see those.
Yeah. My first thought is that potentially what's causing us to not see those higher order resonance, like kind of like the way that Scott had them, and for his oil droplets, is probably due to the fact that these modal structures are very thin. They occur over really small frequency differences. And so if we looked at the data itself, the frequency spacing that we're using probably overlaps the peak and nodal structure, that higher order mode. And so we might be averaging the backscatter over those frequencies. Also, the other thing is these models. So if I'm thinking about the models themselves, and I think about my uncertainty and my bubble size estimates, if I were to plot these models for all the different bubble sizes that I think my bubble could be, that shifts it's a very wide shift. You can see these higher order modes from 160 up to like 200 kilohertz, and they're really thin. So a part of me thinks that we're just averaging them, and so we're just damping that resonance peak in the data itself, and that's why we don't see them. That's what I think. I'm not 100% sure.
Okay, that's interesting. Yeah, I honestly, I don't know what the right answer. I don't know what the right answer to any of these questions is, which is good. That makes me happy. I like mysteries. I'm following along with the answer to the bubbles and sort of the modes. There's a question from Val Schmidt, and this sort of links sort of these data and your models to your third objective. And what Val's saying is that the video of bubbles off the coast of California appear to be quite large. And by that, he means a lot of them might have a very large Ka value, much greater than 1, actually, is what he's saying. And in this area, the models seem particularly poor. He's wondering, does he have that right, do you think? And do you think that will be a challenge?
Yeah, I think he has that. You kind of nailed that one on the head, Val. Yeah, so the bubbles if we looked at that video itself, those bubbles are quite large, and we're insonifying them at frequencies between 160 and 260 kilohertz, which is most likely going to be in that Ka greater than 1 regime. And I think it is going to be a challenge. And I think right now, the question is understanding what is the error, like with the experiments and the results from objective 1. Maybe we can say what the error is, and we can have some sort of a lower and higher bounds to how we go and calculate our gas flux estimates using some of these models later on in platform Holly, when we do want to convert from acoustic measurements to gas flux. I think with objective 1, we can help at least understand where the variations might be coming from.
Yeah, that makes sense. In when you were describing the models, you were talking about that most of the models, at least the Ainsley model and the Clay and Medwin model, that they really only, the assumption is that Ka is less than 1,
Yep.
which makes them small compared to a wavelength, basically. But for the Yeh model, you said that Ka was about equal to 1. Does it not work if it's greater than 1?
I think it's more of just like on the order of 1. So anywhere in the vicinity of 1. I'm not sure what the limitations are on that model. I'm assuming it's somewhere similar to how Anderson would be limited to, because they share similar assumptions. The assumption is just that the size of the bubble just has to be on the same order of the wavelength. It's the same. So if it's too much larger, probably there's some other problems. But I don't think we don't reach that far, I don't think. We're never at Ka of 10 or something, or an order of magnitude larger than 1.
Yeah, okay. You may get close to 10 for those bubbles out in California. They're pretty big. I'm thinking about you're reaching a Ka of almost 1 here on this graph, for a 0.8 millimeter, is that radius? Yeah, so you might get might get up there. I'm actually not sure what the Anderson limitation would be either for, say, a Ka of 10. I assumed that was okay. It's just that Anderson means you have to have a sphere, a perfect sphere, not a spheroid.
Yeah.
Okay, I'm gonna come back and look at the chat here. Let me scroll up here. Make sure I'm not missing something. So this is an interesting question from Kim Lowell, which is, I think just talking at a high level about the different objectives, you've examined deviation from assumed bubble shape, and you're also looking at the hydrate, and I guess you're looking acoustically at assumed bubble shape effects, right? That's objective 1. And then you're looking at dissolution rates related to hydrate. And I think that what Kim is asking is it necessary / possible to examine the interaction between the two?
I think so. With the flow loop device, if we can create different shaped bubbles and create hydrate, we can start to link how hydrate and shape are related to each other.
How about the acoustic aspect of that?
I mean, if we could get a system to insonify them, probably we could do that.
And in fact, I think that was the early objective that we had when we first started doing this with USGS, was to put the acoustic system in the flow loop.
Yeah.
And then I think we were really happy to actually get a working flow loop. It's a challenging lab experiment to do.
Well,
I think it can be done.
Alex did it. I mean, she did the acoustics, but I mean, she didn't talk about the results here, but she actually got some preliminary acoustics. And when I designed the flow loop, I was not thinking well about what the acoustics were actually going to require. So I actually built the flow loop to make it impossible for Alex to get a good signal. So that's my bad.
Yes, it's okay. It's complicated. We're working in a very narrow system, the flow loop device itself. I mean, you could, then I guess the answer is like, you can. The question is, we need probably a different setup currently.
But we do have that now. We got the parts for that. So we can build that out and give it another shot.
Yep.
What is the size of that system, the flow loop system, for the hydrate measurements?
The diameter is 3 or 4 inches. Is that correct, Bill?
The cone goes from about 2 inches down to about 4 inches. So about 3. And the whole thing is about 4 feet tall, 5 feet tall.
4 feet tall. Okay, thank you.
The cone part is only about a foot, but the rest of it is about 4 feet.
So I will say that we built another version of that. I broke it about a year ago, sadly, by dropping it on the floor. But we built another version. So what Bill was talking about was the cone, and what the cone does is it changes the velocity of the water so that it traps the bubble in a center someplace and gives it a happy place that it wants to be in the middle of the cone. And we actually built one without the cone and put together a little PID controller with just a regular webcam looking at the bubble to keep it trapped in the middle and just controlled the motor speed. So there are a couple different ways to do that. It is probably one of the coolest lab devices, I think. I'm biased, but I just think they're really cool lab devices. I'm also rambling, so I'm going to keep asking. I'm going to keep going down the list. So here's one from Scott Loringer, who we were referring to earlier with his backscatter from oil droplets. He's asking, in the Platform Hawley time series data, how will you differentiate between changes in scattering due to changes in flow rate from the seep and changes to the movement of the bubbles? What I mean is, how can you tell if there are fewer bubbles in the acoustic beam because there are fewer bubbles in the water column, or because the bubbles went somewhere else where the echo sounder isn't looking?
That's a good question. I don't. I think one of the things that we can look at with the transducer is looking at, that's a good question. I don't. I think right now I'm not quite sure how I would do that. And probably using additional data from the transducer itself. So looking where the bubbles are moving, if they're moving, they seem to be moving within the transducer or moving out from the transducer. But I think I would need to think about that a lot longer.
Fair enough. And I guess, and I don't know if this is comforting to you, but Scott has just added on to his comment saying that he fully acknowledges that the problem with the experimental design could be his fault. And Scott's saying that because Scott was long involved with everything that we set up out at Platform Hawley when we were here. All right, it's hard to do this without bouncing around, so I'm gonna bounce around a little bit. Let's go back to a question from Ruby. She had a follow-up question to slide 26, and she's wondering what the reasons that xenon has a lower transfer coefficient. And she's asking, is this due to the large molecular weight of xenon compared to methane?
Yeah, so the short answer is yes. The large molecular weight changes significantly the solubility of xenon in the water. So this difference here, while we had similar aqueous concentrations for all of the bubble experiments that we did, this solubility for xenon was much, much larger than air and methane. And so that's what was driving the dissolution in this case. And that's why the mass transfer was so much smaller, because what we ended up doing was just, if we know this concentration difference and the surface area and the shrinkage rate, we can just back out what the mass transfer was. And so this delta C was what was dominating for the xenon bubbles. And so one of the ways to fix this in the future is to make sure that when we're studying all the bubbles, that concentration difference is analogous so that they're comparable to each other.
Alex, I had a follow-up on that. I mean, you mentioned controlling the solubilities. Did you see a difference in the shape of the xenon bubbles relative to the other guys, or did all of the gas bubbles have basically the same shape?
So one of the bubbles, so if we looked at the rise velocity, because it's easier to see here, the one that's on this dirty curve, this one had it was kind of like pancake shaped, while the other ones were, spheroidal, like blobs. And so at least for the rise velocity, that could be what would cause that to have a lower rise velocity. But for the mass transfer coefficient itself, it didn't seem to have an effect in the mass transfer coefficient.
Thanks.
Do they have very different surface tensions?
That's a good question.
That's what Bill's question made me think about.
Right, and that's just not something that goes into that equation, but that's definitely something to look at as possibly being a factor that just doesn't get included in the model very effectively.
Yeah, certainly should affect the shape, right? And then that should affect the bound and everything downstream.
Yeah, exactly. Yeah.
So here's a question from Savannah, kind of a follow-up to Bill's point. Have you or others observed any fluctuations or oscillations in the shape of a single non-spherical bubble as it travels upward through the water column? For example, stretching, tilting of major minor axes, etc. And if so, are there any ways to model or incorporate these changes in the bubble shape so you can obtain a better estimate of rise velocity?
So the answer is yeah, we can definitely see changes in the bubble shape and the tilt as they rise. To incorporate that, I'm not sure. Right now, all we do is take an average estimate and look at the volume, so the volume equivalent bubble radius or diameter. And so that could be a thing to think about in the future as well, trying to see how that might change the rise velocity if they're changing. Trying to,
have you been able to look, for instance, on the image you have on the screen, you can measure the velocity like 1, 2, 3, 4, 5, 6 times there, right?
Yep.
And so one thing you could do, I guess, is have you looked at how
the individual?
How consistent is that velocity, or is it sort of all over the map and you have to average, or are all the numbers about the same?
From what I remember, they're really similar. The uncertainty, the variability from the rise velocity isn't that big. It's probably an order of magnitude smaller than the actual average rise velocity. But I would have to look back. That's a good way to check that.
I would think Savannah's question also has implications in terms of the backscatter too. You'd have to take a approach to the backscatter, much as you think about with fish and things like that. It depends on aspect ratio and how it's presented to the sonar, basically, at any instant.
Yeah, and that's something that we, in the different sizes we've seen in the backscatter, like the larger variability, but I'm not sure if I've seen that kind of large variability in like the rise velocity itself.
Well, that relates specifically to a question that Scott Loringer asked earlier, which is how do you handle incident angle in computing the model scattered for the individual bubbles? So if they're going up with a wobble or a fluctuating tilt, is that incorporated?
In the Yi model, it is. So with the imaging camera itself, during the experiments, we have a sense of how much the bubbles tilted. And so in the Yi model, we can take into account the incident angle of the wave with respect to the bubble. In the field, that would be, you wouldn't be able to do that. But at least in the experiments, we were able to at least get a sense of the influence of the bubble orientation was too.
Yeah, you don't have those linked one-to-one, do you? Do you have the one ping and specifically the tilt for that one ping, and then the next ping the tilt is different, the tilt for that one?
Yeah, not like that. We only understand the variability and the bubble orientation from the imaging. it's not one-to-one. I don't have an image to an acoustic ping.
So how would you incorporate that into the EA model?
Just looking at, so what I would do, or what I have done, is just looking at the range of bubble orientation and modeling. So if I went back to this one, I'm just going to ruin my slide real quick. So if I looked here, this black solid line is the Yi model. This dash black line is the Yi model for a different incident angle. And so what I have done with the Yi model is just, if I have some sense of how much the bubble oscillated or changed in orientation, I can apply some mean orientation to see if the variability of the model itself matches or is on the same order of what we've seen in the data itself.
Yeah, so the black dashed line is, say that one more time, the black dashed line is what?
It's so the black dashed line is the maximum orientation of the bubble. So if the bubble had an average orientation of 0 degrees, that would be the solid line. The dashed line is if it had a maximum tilt of plus minus 15 degrees, that would be what that sigma BS value would be for incident angle of 15 degrees.
Okay.
Yeah.
No, that's interesting, because I'm just coming back to another question from Scott here, where he's asking, could you average over a distribution of incident angles, which I think you kind of answered. And he's asking because he wonders if changes in the incident angle are suppressing the resonant peak or any nodal structure.
Yeah, that certainly could be something that could be happening. I mean, I think that's what we see with the smaller bubbles, not because of the tilt, but because of the fact that the slight changes in size might dampen the resonance. But I think that if you looked at the average estimates from the results themselves, it seems like a very flat curve. And when you look at the Anderson and the Yi model, they tend to have smaller peaks. And I think that the total variation of the different orientations and the different instantaneous variations in the size and orientation do suppress those additional resonance peaks in the data.
So when you're looking at these oblate or prolate shapes, what does the 4 millimeter mean? And this may just be me not knowing more about this subject.
No, that's a good question. It's a question actually that one of the reviewers asked me in the paper edits. So the 4 millimeters is just the volume equivalent radius. So it's
of a spherical. Okay.
Yes, of a spherical bubble. Yep.
Yeah, but that structure and the high frequency backscatter response is just a bit tantalizing, because there's a lot of information carried in there. Just this is maybe why Scott's asking about it too, is that, you know, that structure tells you something about the size and the shape of you know, what you're looking at. It's sort of a bit of a fingerprint, and it's sad to see it get lost place. And it's interesting to think about why that's actually happening.
Yeah. It's one of the perks of oil droplets, I guess.
That's one of the perks of oil droplets. You can also dress your salad with it. So you know,
you can dress a bubble with it too.
That's correct. I'm scanning through to see if there are other questions here that I've missed. You have lots of comments. Congratulations, nice talk. From lots of people. Oh, so there's one other question here. Maybe this is the last one that I didn't get to, and this is from Melissa Melendez, and she's asking, do you have measurements of dissolved methane in seawater? And Melissa, of course, you can unmute yourself. I'm assuming she means in at coal oil point, like in the water at coal oil point.
Yeah. I don't, but I think the people that we work with, Dave and the group, most likely have some information about the dissolved concentration of methane in the water column and other hydrocarbons, as other people had mentioned, that potentially exist in the area too.
Yeah. Yeah, and to do a model there, you also need to know all the other gas constituents, right? Because that mass transfer rate can be negative. We can grow bubbles this way too, and that's part of what we're seeing, I think.
Yep.
All right. Other questions from the audience here? Oops, hang on. Yes, Melissa's just confirming. Okay, then I think that what we'll do is end this section of the presentation. Thank you again, Alex. I think that was a really interesting talk. And I think that, right, we should be clapping. So well done. And I think we will go to this sort of the second session. I think the committee maybe will meet amongst ourselves quickly. And then if you can just stand by, I'll send you a note to join in.
Yeah, you should have access to the Zoom link that I sent out, the host.
So I think if I'm not correct, and I'll go double check, but I think, Alex, that in your email to everybody, you shared 2 Zoom links.
Yep, the second was for that.
Right. So this is the first one, and then we'll go to the second one. So if I guess at this point we'll end this one, and for the committee, we'll go to the second one. And as I said, Alex, I'll just shoot you a quick note when we're ready for you to join us. That's
Awesome.
okay.
Yep, sounds good.
Thanks, Alex. And thanks everybody for joining in
Thank you.
and the great questions.